Hello students, to begin with, let us see to the solutions for the questions I gave you in the previous session. Question number 1, limit x plus 1 raised to 5 minus 1 upon x as x tends to 0. Here, we cannot put the limit directly in the given function as it is of the form 0 upon 0. Here, we will use limit x to the power n minus a to the power n upon x minus a is equal to n a raised to n minus 1 as x tends to 0. For limit x plus 1 raised to 5 minus 1 upon x as x tends to 0, let x plus 1 be equal to h. That is, when x tends to 0, then h will tend to 1. Therefore, limit h to the power 5 minus 1 upon h minus 1 as h tends to 1 is equal to limit h to the power 5 minus 1 to the power 5 upon h minus 1 as h tends to 1 is equal to limit 5 into h power 5 minus 1 as h tends to 1 can be simplified as 5 into 1 to the power 4, that is equal to 5. Note that you should not forget to change the limits here. See to the solution for question number 2, limit 3x square minus x minus 10 upon x square minus 4 as x tends to 2. For the solution, it is again not directly solvable by putting the value of x is equal to 2. Firstly, we will factorize the numerator and denominator by splitting the middle term and cancel the common factor and then put the value of x. Look here, limit 3x square minus 6 minus 5 into x minus 10 upon x minus 2 into x plus 2 as x tends to 2 can be simplified as limit 3x square minus 6x plus 5x minus 10 upon x minus 2 into x plus 2 as x tends to 2. That can be solved as limit 3x into x minus 2 plus 5 into x minus 2 upon x minus 2 into x plus 2 as x tends to 2. On further simplification, we have limit x minus 2 into 3x plus 5 upon x minus 2 into x plus 2 as x tends to 2. We have seen here x minus 2 is common, so we can cancel them out and we have limit 3x plus 5 upon x plus 2 as x tends to 2. That is equal to 3 into 2 plus 5 upon 2 plus 2, that is equal to 6 plus 5 upon 4, that gives us 11 upon 4. Please note that the common factors will be cancelled only in the limit, but in a function you do not cancel directly until it is in an indeterminate form. Now, question number 3, limit cos 2x minus 1 upon cos x minus 1 as x tends to 0 can be solved here. We see that when we put the limit, it is of indeterminate form. Firstly, we will use the formula 1 minus cos 2x is equal to 2 sin square x and simplify it and then put the limit. Look how we solve here, limit cos 2x minus 1 upon cos x minus 1 as x tends to 0 is equal to limit 1 minus cos 2x upon 1 minus cos x as x tends to 0 can be written as limit 2 sin square x upon 2 sin square x upon 2 as x tends to 0, because 1 minus cos 2x is equal to 2 sin square x and 1 minus cos x is equal to 2 sin square x upon 2. Now, multiplying and dividing by x square and then multiplying by 4 upon 4, in the numerator we have limit sin square x upon x square into 4 into x square upon 4 upon sin square x upon 2 as x tends to 0 can be rewritten as limit sin x upon x whole square into x upon 2 upon sin x upon 2 whole square into 4, that is equal to 1 into 1 into 4, that gives us 4 as the answer. Now, let us discuss about limits of trigonometric functions and some beautiful theorems. Let us first discuss about the limits of trigonometric functions. The following facts stated as theorems about functions in general come in handy in calculating limits of some trigonometric functions. Theorem number 1, let f and g be two real valued functions with the same domain such that f of x is less than or equal to g of x for all x in the domain of definition. For some a, if both limit f of x, x tends to a, and limit g of x as x tends to a exist, then limit of f of x as x tends to a is less than or equal to limit of g of x as x tends to a. This is illustrated in the figure, see on your monitor. Here in the graph, notice this is your x axis and this is y axis. Here the graph y is equal to f of x and this is the graph of the function y is equal to g of x and this is the point A. Now, theorem number 2, which is also known as sandwich theorem, let f, g and h be real functions such that f of x is less than or equal to g of x, which is less than or equal to h of x for all x in the common domain of definition for some real number a. If limit of f of x as x tends to a is equal to L, that is equal to limit of h of x as x tends to a, then limit g of x as x tends to a is equal to L. This is illustrated in the figure. Look at the monitor. This represents your x axis x dash o x and this is your y axis y o y dash. You can see the three functions in the graph. Y is equal to f of x, y is equal to g of x and y is equal to h of x, and this is the common point A. Some more theorems which we use here are the following are two important limits. First, limit sin x upon x as x tends to 0 is equal to 1, and second, limit 1 minus cos x upon x is equal to 0 as x tends to 0. A general rule that needs to be kept in mind while evaluating limits is the following. Say, given that the limit f of x upon g of x as x tends to a exists and we want to evaluate this. First, we check the value of f of a and g of a. If both are 0, then we see if we can get the factor which is causing the terms to vanish. That is, see if we can write f of x is equal to f1 x into f2 x, so that f1a is equal to 0 and f2a is not equal to 0. Similarly, we write g of x is equal to g1 x into g2 x, where g1a is equal to 0 and g2a is not equal to 0. cancel out the common factors from f of x and g of x if possible, and write f of x upon g of x is equal to p of x upon q of x, where q of x is not equal to 0. Then limit f of x upon g of x as x tends to a is equal to p of a upon q of a. Now, let us discuss about derivatives in detail. Now, to discuss about derivatives, we have seen that by knowing the position of a body at various time intervals, it is possible to find the rate at which the position of the body is changing. It is of very general interest to know a certain parameter at various instants of time and try to find the rate at which it is changing. There are several real life situations where such a process needs to be carried out. For instance, people maintaining a reservoir need to know when the reservoir overflows, knowing the depth of the water at several instances of time. Rocket scientists need to compute the precise velocity with which the satellite needs to be shot out for the rocket, knowing the height of the rocket at various times. Financial institutions need to predict the changes in the value of a particular stock, knowing the present value. In these and many such cases, it is desirable to know how a particular parameter is changing with respect to some other parameter. The heart of the matter is derivative of a function at a given point in its domain of definition. So, students, today we discussed about limits of trigonometric functions, some important theorems. In the next session, we shall study more in detail about derivatives. Thank you.